Before we talk about what Jupiter is made of, we need to establish just how extraordinary its size actually is, because I don't think any of us truly grasp it intuitively. Jupiter is not just the largest planet in our solar system, it is more massive than every other planet in the solar system combined, all of them. Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, add them all up, and Jupiter still outweighs them. That's not a slight advantage, that's dominance on a scale that's almost philosophically unsettling. Here's a comparison that might actually land. If Earth were the size of a grape, Jupiter would be a basketball. Now hold a grape in one hand and a basketball in the other and really think about that. 1,000 Earths would fit inside Jupiter's volume, 1,000. And yet, despite this unimaginable size, Jupiter rotates faster than any other planet in the solar system. A full day on Jupiter lasts less than 10 hours. Something the size of a basketball is spinning so fast, its day is shorter than your workday. That speed of rotation has enormous consequences for what happens inside the planet, and we'll get to that. But first, we need to talk about how this thing even came to exist, because there are two competing theories, and neither one of them is quite as satisfying as we'd like. The first theory, the one most of us were taught, goes something like this. In the early solar system, there was a massive rotating disk of gas, dust, rock, and metal, all swirling around the young sun. Over millions of years, bits of material started clumping together. Small clumps attracted more material. Bigger clumps attracted even more. Gravity kept compounding on itself. Eventually, one of those clumps grew so massive that it had enough gravitational pull to start vacuuming up enormous quantities of gas from the surrounding disk, and it just kept doing that for billions of years until it became Jupiter. Under this model, there would be a solid rocky and metallic core somewhere deep inside the planet, a kind of seed around which all that gas accumulated. The second theory is wilder and, frankly, more poetic. In this version, Jupiter started life as a completely separate, enormous cloud of gas sitting just outside the early solar system. Over time, that cloud became so large that it collapsed under its own gravity, the same basic process that forms stars, except in this case, the cloud wasn't quite big enough to ignite into a star. So instead of becoming a sun, it became a planet, a failed star. And eventually, the gravity of our sun pulled it in and settled it into an orbit. Under this theory, Jupiter wouldn't really have a structured core at all. It would be more like an enormous layered ball of compressed gas. Here's the maddening part. We're still not entirely sure which theory is correct, and finding out is part of why the missions to Jupiter over the past few decades have been so important. In science, some of the greatest breakthroughs come not from meticulous planning, but from spectacular accidents. And in July of 1994, the universe handed us one of the most extraordinary accidental experiments in the history of planetary science. A comet called Shoemaker-Levy 9 had been captured by Jupiter's gravity and was on a collision course with the planet. And not a gentle collision. This comet, which had already been torn into roughly 24 pieces by Jupiter's gravitational force, was traveling at 216,000 kilometers per hour. The largest individual fragments were around 2 kilometers across. To put that in perspective, the asteroid that wiped out the dinosaurs is estimated to have been about 10 to 15 kilometers wide. These comet fragments were smaller, but what they lacked in size they made up for in number and velocity. Now here's where the story gets almost unbelievably convenient for science. Collisions like this are estimated to happen once every 6,000 years. We happened to be alive for one. We happened to have the newly operational Hubble Space Telescope ready and pointed at Jupiter. And almost impossibly, we happened to have a spacecraft, the Galileo probe, literally en route to Jupiter at that exact moment, approaching from an angle that gave it a clear view of the impact zone. You simply cannot script a coincidence like that. There were 21 separate impacts over 6 days. The largest single collision released energy equivalent to 300 million atomic bombs. Let that number sit for a moment. 300 million. It was the largest explosion ever captured on camera,
and the aftermath was visible from Earth-based telescopes as enormous dark scars across Jupiter's cloud layers. These weren't small marks, they were each roughly the size of Earth, just sitting there as bruises on the face of the giant. But the scientifically priceless part of this event was what the Galileo spacecraft saw as it flew through the material that had been ejected from Jupiter's interior. For the first time in human history, we were looking at matter from beneath Jupiter's cloud layer, material that had been buried deep inside the planet, flung out into space by the violence of the impact, and now floating freely where our instruments could study it. And what did we find? Water. An unexpected and significant amount of water, which raised immediate and profound questions about what else might be lurking beneath those clouds. Water meant chemistry. Water meant complexity. Water meant the interior of Jupiter was not the simple ball of compressed gas that anyone had assumed. That discovery set the stage for the mission that would fundamentally rewrite our understanding of the solar system's largest planet.
The Juno spacecraft launched in 2011 and arrived at Jupiter in 2016. Its mission was specific and ambitious: get close enough and stay close enough to map the interior of Jupiter with enough precision to finally answer the core question. Literally, what is at the core? What Juno confirmed, and what we've spent the years since trying to fully comprehend, is that Jupiter is not a gas giant. It is covered in gas. The outer layer of clouds, made primarily of ammonia and water vapor, is spectacular and complex, but it's thin. Relatively speaking, those iconic swirling clouds extend only about 50 kilometers deep. On a planet 70,000 kilometers in diameter, that's barely a skin. Let's walk through the layers properly, because each one is stranger than the last. At the very top, in those clouds, the temperature drops below -100 degrees Celsius. Water ice crystals mingle with ammonia, which acts as a natural antifreeze, allowing liquid water to exist at temperatures that would freeze it solid on Earth. These droplets collide with ice crystals, building up electric charge, and the result is lightning. Not our modest terrestrial lightning. Jupiter produces lightning storms of extraordinary scale, raging continuously across the cloud layer. The ammonia and water eventually clump into slushy hailstones that fall downward into the lower atmosphere, melt into rain, evaporate, rise again, and repeat in a continuous cycle that has been running for longer than Earth has existed. The Great Red Spot, which you've certainly seen in photographs, is a storm system that has persisted for at least 350 years. It is wider than Earth. It extends hundreds of kilometers downward into the ammonia rain layer, and it reaches upward higher than any other cloud formation on the planet, absorbing more ultraviolet light from the sun, which triggers chemical reactions that produce that distinctive deep red color. It is not a surface feature. It is a vertical column of violent atmospheric activity stretching from deep within the atmosphere up above the standard cloud level. Imagine a cloud formation 10 times taller than Everest and 10 times deeper than the ocean, and you still haven't captured it. Below the clouds, as you descend, the temperature climbs. This is crucial to understand. The heat down here is not coming from Jupiter's proximity to the sun. It's coming from pressure. Gravity is so intense that it compresses everything, concentrating molecular energy, generating heat. The deeper you go, the more pressure, the more heat, in a relationship that produces effects that simply don't exist anywhere on Earth. At around 1,000 kilometers below the cloud layer, something extraordinary happens. The hydrogen gas, which makes up the vast majority of Jupiter's atmosphere, stops being a gas. The pressure becomes so overwhelming that the hydrogen molecules are forced into contact with each other continuously, with nowhere to go and no way to maintain the spacing that defines a gaseous state. The hydrogen becomes liquid, not because it got cold, the way we liquefy hydrogen on Earth, but because the pressure raised its boiling point so high
that it can exist as a liquid even at temperatures exceeding 1,000 degrees Celsius. Temperature and pressure are doing something here that has no everyday analogy. What you have at this depth is the largest ocean in the solar system, an ocean of liquid hydrogen, roughly 20,000 kilometers deep, 2,000 times deeper than Earth's deepest ocean. And it is an ocean without a surface. There's no shoreline where the gas meets the liquid. The transition is so gradual, so continuous, that there's no defined boundary. You would pass through it without knowing you'd crossed into a different state of matter.
Now we go deeper, and this is where Jupiter stops being merely strange and starts being something that challenges our intuitive understanding of what matter even is. As we descend through that liquid hydrogen ocean, the pressure continues to build. We're talking about pressures millions of times greater than what we experience at Earth's surface. And at the bottom of that ocean, at temperatures around 10,000 degrees Celsius, something happens to hydrogen that has no parallel in our everyday experience. The electrons that normally orbit hydrogen atoms, bound tightly to their nuclei in the way we learn in chemistry class, are squeezed so hard that they're forced away from their atoms entirely. They stop belonging to any individual atom and begin flowing freely throughout the liquid. If you know anything about electrical conductivity, you already know what this means. Free-flowing electrons are exactly what makes metals conduct electricity. Copper conducts electricity because its electrons move freely. So does silver, so does gold, and so does hydrogen when you put it under millions of atmospheres of pressure. This is metallic hydrogen. It is still liquid. It does not look or behave like steel or iron in any way we'd recognize. Think of it more like mercury in a thermometer, a liquid that conducts electricity. And it exists in a layer roughly 40,000 kilometers deep, making up the majority of Jupiter's interior. The metallic hydrogen layer is also responsible for one of Jupiter's most powerful characteristics. As Jupiter rotates, and remember, it rotates incredibly fast for its size, this massive electrically conductive liquid spins with it. A spinning electrically conductive material generates a magnetic field. This is the same basic principle as an electric generator, and Jupiter's magnetic field is the result, the most powerful planetary magnetic field in our solar system, roughly 20,000 times stronger than Earth's. Its influence extends so far into space that if you could see it, it would appear larger than the full moon from Earth's surface. So what's at the very center, beneath all of this? This is where things get philosophically interesting, because the honest answer is that we're not entirely sure, and what we do know is stranger than what anyone expected. For a long time, the working model was a compact, dense, solid core of rock and iron, something roughly the size of Earth sitting at the center of everything. It made sense mathematically. Heavier elements sink. They would have accumulated at the center over billions of years and formed a solid ball. Clean, simple, logical. But the data coming back from Juno is telling a different story. The core of Jupiter appears to be what scientists are now calling fuzzy. And they don't mean that term loosely. What they mean is that the boundary between the metallic liquid hydrogen layer and the solid core doesn't seem to exist as a clear line. Instead, the two states of matter blend into each other. Heavy elements and lighter ones mixed together in a region that spans roughly half of Jupiter's total radius. Not a solid core inside a liquid mantle, more like a dense, hot, stirred soup of liquid, rock, and metal, with no defined beginning or end. This is a completely different picture of planetary interiors than anything we'd modeled before, and it raises an immediate question. How do you get a fuzzy core? How does the inside of a planet become this thoroughly mixed?
The leading hypothesis is violent and dramatic, which feels appropriate for Jupiter. Scientists believe that early in the solar system's history, a young protoplanet, roughly 10 times the mass of Earth, may have been on an intersecting orbit with Jupiter. And at some point, it didn't just pass close, it hit. A head-on collision, or something close to it, between a massive rocky body and a young Jupiter. The energy from an impact like that would be staggering. It would scatter the solid core material outward, mixing it with the surrounding material, diluting it, creating the diffuse, extended region of mixed matter we now observe. This single collision could also explain something else that's puzzled scientists, which is how Jupiter grew so large so quickly. A massive impactor bringing its own heavy elements and triggering gravitational dynamics that allowed Jupiter to pull in even more material from the surrounding disk. The collision theory is compelling, but here's where science has to be honest about its limitations. Researchers ran computer simulations of exactly this scenario. They modeled planets of different sizes hitting a young Jupiter from different angles at different velocities, hundreds of simulations looking for the one that produces the fuzzy core we observed, and the results were humbling. Every single simulation that produced a fuzzy core from a collision also showed that core gradually restabilizing and solidifying into a compact ball over time. The mixing didn't persist. The physics kept trying to clean things up and return to a neat, layered structure. So we know the fuzzy core is real because the data says so. We know the collision theory is plausible because the physics says so. But the simulations can't actually produce a stable fuzzy core that lasts billions of years, which means either our simulations are missing something, or the collision isn't the full explanation, or the answer is something we haven't thought of yet.
And that's the thing about Jupiter that I find most profound, the thing that makes it more than just a science story. It's a reminder of what genuine knowledge actually looks like. We send spacecraft across hundreds of millions of kilometers of space. We flew one directly through the debris of a comet impact. We put another one in polar orbit around the planet specifically to decode its interior. We built instruments capable of measuring gravitational variations so subtle they can infer the density of material 40,000 kilometers below the cloud tops. And after all of that, after decades of effort and billions of dollars and the work of thousands of brilliant people, our answer to what is Jupiter's core and how did it form is essentially, we think we know, but we're not completely sure, and the simulations don't quite work out yet. That's not a failure of science. That's what science actually looks like at the frontier. It's honest uncertainty. It's the acknowledgement that the universe is under no obligation to be simple or to match our models. Jupiter has been here for 4.5 billion years. It was strange long before we had words for strange, and it will keep defying our expectations for as long as we keep looking. The next time you see Jupiter in the night sky, that bright, non-twinkling point of light that outshines everything except the moon and Venus, take a moment to think about what you're actually looking at. Not a ball of gas, a world of liquid hydrogen oceans, a metallic interior generating a magnetic field the size of a small star, a fuzzy, churning, unresolved core that physics itself can't fully explain, a mystery that is 4.5 billion years old and still not solved. That's Jupiter, and it is extraordinary.